let's get started. I think Misha has a lot of slides. Okay, so
That's not so funny. It was not my fault, actually.
Yeah, it's cool too. So we are honored to have Misha Lukin today give the PSC. Misha did his undergrad at Moscow Institute of Physics and Technology, and then moved to the US to Texas A&M University, did a PhD with Marlon Scully. And after a brief postdoc at Texas A&M, he moved to Harvard to become a postdoctoral fellow at the I-Temp Institute. And then some time afterwards, he became a faculty at Harvard in 2001. And since has been there. Misha has won like a zillion of prizes that I don't want to name all of them. So he won a Sloan, Packard, NSF Career, APS Rabi Prize, and very recently Willis Lamp Award for Laser Science and Quantum Optics. Misha, broadly speaking, has made seminal contributions in what I would call quantum sciences, and also more recently in biological sensing. He's extremely broad in his research. He is one of the few people who works with atomic systems and solid-state-based systems, so that's extremely rare in our community. He's also working both in theory and experiment, and as such has been an idol for me since I was a master's student or undergrad already, honestly. And so without much further ado, I would say, give it to Misha.
So I'd like to start, thanking Oscar and Manuel for invitation, and Manuel also for a very nice introduction. So it's actually great to be here. I think I visited last time was quite a few years ago, and it's fantastic to see the new faces and to actually quite inspiring, I must say. So, what I'd like to do today is to talk about our work in the kind of new field of quantum science. And basically, this field is based on the premise that information, its acquisition, storage, and transmission and processing involves fundamentally physics. And it is also very clear that, with all of this kind of recent technology developments, the ultimate elements of sensors, processors, and transmitters, eventually will be of quantum size. And so it is actually kind of interesting to wonder if, kind of single atoms can be used as memory or as information processors. And, and indeed, it turns out that fundamental constituents of matter, such as electrons, nuclei, photons, can actually acquire, store, and process the information. And there are some unique features which become accessible, once you go to this kind of micro scale. And in particular, one can think about, for example, using the spin of electron or nuclei to encode a qubit. And of course, we can orient the spin either up or down, and that way we can encode 0, 1. But basically, everyone knows that if you really work with this kind of elementary particles, you can also create superposition of states. So, for example, if you orient the spin along the x direction rather than z direction, you will create a superposition of the particle simultaneously in a state spin up and spin down. And these quantum superpositions are actually very special to the quantum world, and actually they enable some very unique, interesting features for both kind of new physics and actually also new applications. So I must say I have one slide, since it's a colloquium talk, I kind of, often, do a little bit of kind of, introduction of this basic concept. I don't know, I think at Caltech, even undergraduates don't need this, but I will tell these slides because it has a little bit contemporary meaning, I'll show this slide. So, and actually, how to understand the superposition, we can go back in history and remember one of the Soviet leaders, who was a colorful leader. His name was Nikita Khrushchev. And he once came to the United States to participate in the United Nations Assembly, and it was when he was banging the shoe. It was very famous kind of accident. But during that time, he also did other things, which I'm not going to go into. But one of them is he gave some interviews to friendly newspapers. And these newspapers, they know that he likes to talk a lot. So they asked him, so can you tell us briefly in one word, what's the state of Soviet economy? And his answer was, good. But, so, okay, can you tell in 2 words? And he says, not good. So actually, I'm actually surprised that you guys are laughing, because in modern days, with all of this fake news, this is actually pretty common, and it's not very good, But actually, in quantum mechanics, being in this kind of superpositions of these 2 answers is actually quite common. And this is actually, pretty good. So in fact, this kind of, fundamentally, this idea of superposition is essentially behind all of these kind of things that you hear about, quantum science and quantum information. So for example, if you use superpositions to process many inputs in parallel, you end up getting the so-called quantum speedup, and this is, the foundation of quantum computing. So if you use quantum superposition to encode a bit of information and send it, then, in this case, unless you know exactly the basis in which you encode, you cannot measure the system without disturbing it, and it's a basis for quantum communication. Finally, these superpositions, especially if you involve many particles, are actually quite fragile. So that actually, this is the reason why quantum computers are so fast, so difficult to build. But at the same time, one could turn things around, and you say if you kind of use this fragility smartly, you could maybe build some novel quantum sensors. And this is the basis for the field of quantum metrology. So motivated by this consideration, there is now kind of a broad quest for what I would say controlling quantum world. And in this quest, what researchers are trying to do is they're trying to isolate and control some simple quantum objects, and then just, kind of try to use these simple quantum objects as building blocks to build more and more complex quantum systems from them. And, what is the hope? The hope is that we should be able to do new physics with them. And, for example, one, kind of idea is we can use this as building blocks to create new states of matter and explore them, the states which don't occur naturally. But, also, of course, the hope is that we could try to, realize these kind of interesting applications, for example, quantum processing, communication, and metrology. So in this talk, I will really focus on this kind of new physics aspect. But one thing that I would like to say right away, and I hope I can illustrate it with examples, is that all of these directions are closely connected. So basically, kind of developing better control techniques allows us to kind of create and probe kind of more and more complex states. And, that itself might actually enable us to really start doing kind of, exploring new applications, like exploring new quantum algorithms and, possibly build things like better sensors, for example. So I guess this is not the first talk about, quantum computing, quantum information in this audience. And so I guess you guys know now that there are many kind of platforms, many directions which are being explored to realize these systems. And so you could think about this as a kind of ultimate quantum rivalry where, maybe different, systems are trying to actually, kind of in a race, trying to outperform each other. But actually, if you think about this for a second and think about maybe more in a kind of Eastern philosophical way, then you realize that this rivalry is not between individual systems, but really between different forces of nature. And these forces of nature, are, basically the competition between the controllability and scalability. So that's certainly kind of a big challenge in the quantum world to combine these two, but it's actually, much more general than that. So, for example, if you think about, organization where you actually, hire, kind of many, smart, people like physicists, put many of them together, right? That such an organization will actually become very difficult to control, So you never know what will come out of that. And so this is like actually, there's in many cases it's like this, and I think, this quantum information is just one manifestation. So basically, the current challenge is that really we would like to kind of build systems which can perform tasks that, cannot be efficiently simulated on kind of modern classical computers. And that, requires that we work with, system sizes of maybe, 30, 40, 50, or larger number of like fully controlled qubits. So the question is now, so if we build these machines, what will, we learn? What will be the outcome? And, I would like to kind of at least express my opinion. In my opinion, so the first things that we will start learning will be about physics of this kind of more complex quantum systems itself. And actually one specific aspect which I think is really quite intriguing and which we already start to enter is this kind of connection between two areas of physics, each of which is really, we teach, as basically first undergraduate kind of classes. So on one hand, we learn about quantum mechanics, and we learn that it's perfectly kind of reversible, everything should be coherent. And that's what we learn in Quantum Mechanics 101. Then in Statistical Mechanics 101, we learn things like equilibrium postulate, we learn things like thermal ensemble, we learn about phases of matter. And if you think about that, okay, so what's the connection between the two? So where does this first description, ends, and where does the new description start? So basically, as we increase the sizes of quantum systems, we can really take a peek into how and when this kind of process is happening, what's the dynamics, and basically in the process of that, what we really would like to do is to understand many body non-equilibrium dynamics. We would like to understand the concept of thermalization better. We would like to understand the role of localization, long-range interactions, non-local interactions. And at the end, we hope that we can really find in this kind of new big Hilbert space, which we have, we can really find some new islands where maybe we'll find some new states of matter which are far away from equilibrium. And if we find them, perhaps it can be also useful to realize this, new applications, such as information processing and metrology. Okay, so with this kind of, within this general setting, what I would like to do today is I'd like to talk, if time permits, about two topics. On one hand, in the first part, I would like to actually talk about our sort of approach to kind of controlled, approach towards building, quantum matter, if you want, building, kind of quantum computers or quantum simulators. And so I will tell you about kind of new approach which we are exploring towards realizing this goal, which makes use of atom-by-atom assembly of strongly interacting arrays of particles. And I will tell you how we can use a system to actually implement a programmable spill model and actually explore that, and I will tell you also about some first kind of unexpected discoveries which we kind of make with this system, in particular, really, observing some kind of new robust quantum dynamics. So in the second part, I would like to shift gears. So if you got bored with quantum computers, I will talk about time crystals, and I'll tell you a little bit what's kind of the idea of this time crystal, and then tell you about an experiment, a completely different system, a system of kind of coherent but completely disordered qubits, if you want, where we actually can observe this time crystalline order, and perhaps I can even have time to tell you about when this time crystalline order can be useful, and this involves applications in metrology. Okay, so let me focus on this first part of my talk. And this first part of my talk will involve building quantum processors based on neutral atoms. So neutral atoms have a lot of advantages, a lot of useful features. So in particular, they are well known for having excellent coherence properties. If you want an example, think about optical atomic clock, which is actually now, one of the sort of most precise instruments, that humankind ever built. The second, also important ingredient is actually it's very easy to create, samples with large number of atoms. Just here around us in the air, there are a lot of atoms, and most of them are neutral, so it's very good. So these atoms also can strongly couple to light, but yet, kind of this neutral atom platform does not always come to mind as most natural in terms of, for example, building a quantum machine. And there are two reasons for that. So on one hand, neutral atoms, especially in the gas phase, interact very weakly. And also neutral atoms are becoming very difficult to control individually, especially if you have a large number of them. And this is true if you want to kind of illustration of that, you should think about wonderful experiments in optical lattices and quantum gas microscopy, and visit one of the labs to just see how challenging this is. So what we would like to do is we would like to try to address both of these problems at once, and to do that we actually started exploring a new approach in which we really build kind of matter atom by atom. So in this approach what we do is we start with the gas of pre-cooled atoms in a gas phase in a vapor cell, and then shine tightly focused beams of light which actually attract the atoms towards the intensity maxima, towards a focal point. And these things are called optical tweezers. So optical tweezer is a very well-known technique. It's used in atomic physics and biophysics in many areas. What we would like to do in this approach, we would like to focus these laser beams very, very tightly, such that at most there is one atom in each tweezer. So like basically two atoms do not fit. If you end up with two atoms, they just get ejected. And then what we'll do is we'll actually have a lot of these tweezers. We will actually have over 100 of these tweezers and just focus them into this vacuum chamber and just try to load them all. But this system has a lot of entropy, so in each given shot what will happen is that some of the tweezers will be loaded and some will be empty. So to get rid of this entropy, we use the idea similar to kind of a Maxwell demon. So what we'll do is just simply take a picture of these atoms, figure out which traps are full and which are empty, and just remove the empty trap and then rearrange the other tweezers to create a desired arrangement of atoms. Once this is done, all we need to do is to engineer the interaction between these atoms. So typically, these atoms will be spaced by distance on the order of a micron or few microns. So basically, to make them talk to each other, we can use two approaches. One of them is we can excite these atoms into the so-called Rydberg states. So Rydberg states is highly excited states of atoms where the atom size is very large. So at this point, the atoms start feeling each other, and start interacting in a controlled way. The other approach, which we pursue also in a separate experiment, involves coupling these atoms by means of photonic waveguides. This is actually also very intriguing directions, which also have kind of many advantages, in some ways. But in today's talk, I will focus on this first approach. So here is kind of a schematic of experimental setup, and the key element of this setup is this element called acousto-optic deflector. And what it does, it basically is a device in which one laser beam goes in, and you drive this device with a set of different radio frequency tones. Then for each of the tone, you get the light deflected by a certain angle. So then what you do, you just take these beams and then focus it into this vacuum chamber, and then basically load the atoms. Then through another objective, take a picture of this atom, activate this feedback procedure exactly as I discussed. So this is, currently the team, working on this project. But I would like to actually acknowledge the contribution of one special individual who is your wonderful and esteemed colleague, Manuel. So thanks to the generosity of, the search committee or Maria personally, he was allowed to, spend some time in my lab, and during that time, moreover, not only he was allowed to do some adventurous things. So basically, when we started doing it, it kind of seems like a good idea, but it was really absolutely not clear how well this will work. And actually, this really turned into kind of a wonderful, project over a very short period of time. And I think Manuel really should get a lot of credit for starting this effort. Without him, this wouldn't happen. So, okay, but let's now see at the result. So basically, here what I'm showing is a kind of slowed down movie of the two consecutive images where we first load about 100 of these traps with atoms, and what you see is that initially this so there are single shot images of atoms, so this loading is completely random initially, and then what we do is just we move the atoms to the left, and basically this ends up with the pretty regular array. So there is one kind of hole here, but it is working pretty well. So what we can also do, we can, of course, we don't have to, we can create a desired pattern of atoms. For example, what we can do is we can try to create pairs of atoms, and these are again single shot images of the pairs, or we can create clusters of 10. And what I would like to point out here is that these clusters are not perfect. So for example, here it looks like one atom is missing, maybe here one atom is missing, but actually they are pretty good. So we can really do this very fast and with very high fidelity. And of course, what we can also do, we can actually vary the geometry with each repetition, and for small contribution to Lukin lab, we can write your name in a specially patented Atomica font. Yeah. But so far it's completely classical. These are non-interacting atoms. There is there's nothing quantum here. So basically now what we need to do, we need to add the interactions between the atoms, and in order to do it, we will excite the atoms into the Rydberg state with high principal quantum number on the order of 100 or so. And at this point, what we will do is we'll make use of special properties of Rydberg atoms, namely their long lifetime and very strong interactions. And just to give you a little bit of a sense is that for n equals 100, the van der Waal interaction between atoms is 14 orders of magnitude larger than the interaction between the ground state atoms. So 14 orders of magnitude is a good number. It's very big, And so what it really means is that if these atoms are far away and we, for example, drive these atoms coherently, they can undergo kind of conventional Rabi oscillations. But if we bring these atoms close, what will happen at some point is interaction will take over. And so what it means is that if you try to excite these atoms resonantly, you will not be past certain distance, you will not be able to do it. In this case, you will be able to excite one atom, but never two. So this phenomenon is known under the name of Rydberg blockade, and basically what this means is that basically simultaneous excitation of pairs of atoms is blocked at certain distances, smaller than some number on about few microns. And that's the essence of this dipole blockade or Rydberg blockade. So basically, if you have a cloud of atoms within this blockade, only one of them can be excited, and one can actually then, in this case, even think about coherent processes which will involve transitions between the states where all atoms in the ground state and just one of them excited, and this process will be restricted to this kind of two-dimensional subspace effectively. Note that characteristic kind of feature of that is that the probability of excitation should increase with n, and hence Rabi frequency should also scale as a square root of n. So that's the essence of this Rydberg blockade. I must say that these are the ideas which go back something like 17 years, 16, 17 years, and since then they have been actually explored by many groups for many different applications. And actually I must make a confession that this is sort of the experiment I was thinking about when I was just starting as a junior faculty at Harvard. But at the time I decided it's maybe actually kind of a little bit too challenging. So it really required people like Manuel to really, go back to that. So we can easily combine this blockade effect with our atom arrays. For example, what we can do, we can just excite the atom in the Rydberg state along the array direction. So we excite it through the two-photon transition, but it's not so important. But what we can do is now we can, for example, prepare the clusters of atoms, either individual atoms or pairs of atoms or free atoms. And so long as they are very close together, what we end up, in all of these cases, we end up with creating at most one excitation. But what you see is that basically the Rabi frequency is enhanced. So it's precisely the signature of this kind of Rydberg blockade. And actually it's good to think about this Rydberg blockade as a kind of coherent constraint. So basically what, you constrain your system dynamics to this one excitation. So that's actually a very kind of important take-home message. So once this constraint is broken, then, this picture is no longer perfect. So it's actually some interesting, more complex dynamics results from that. And we will now try to explore this a little bit, Yes?
So the error on the last point there with the 5 is,
yeah.
I can see it. On the others, it's negligible. But so does this mean that as you go to more and more, you will have bigger errors there? Or what
No. So this means that this is a blockade radius. So the free atoms are still blockaded. But then the fourth and fifth is already beyond the blockade. So something funny starts to happen, and we will now talk about this. In fact, the rest of my talk will be exactly about this kind of.
And your line there is just a frequency.
It's a square root of n. It's square root of n. Okay, so basically, you know, what I'd like to do now is I'd like to use this system for something kind of interesting, and actually in this, you know, esteemed establishment, including this auditorium, you know, of course, we have to kind of remember that this entire kind of business of quantum computing started with pioneering ideas of Feynman, where he kind of thought about how to actually model quantum systems. And basically modeling quantum systems is very hard because, you know, n quantum system require two-state quantum system requires solution to n coupled equation. But the alternative approach is to basically implement the model of interacting system on a quantum simulator or the other kind of other quantum system using the standard set of qubits with some kind of programmable interaction. And what I'd like to show is that we can, using our approach, we can exactly do that, you know. So specifically, let's now consider the system involving our atom array, which will excite to the Rydberg state. And, you know, the Hamiltonian for the system will involve the following. It will involve some kind of coherent excitation, you know, going from ground state to Rydberg state. It will also involve effective detuning of this laser field. And this effective detuning is like a magnetic field in the z direction. And then there is also this interaction term, which is responsible for blockade. So we can take this model and, for example, ask a question, what's the ground state of this model? So this model, by the way, is kind of isomorphic to Ising model. So we can ask what's the phase diagram corresponding to the ground state. And so we can actually parameterize it with two parameters. One of them is detuning, is this field in the z direction, if you want. Another one is an interaction range. How, you know, how long range is the interaction between the atoms. So focusing first on this first term, you know, if this detuning is negative, it's clear that, you know, basically n should be 0, right, because it's the most favorable term. So it means that all atoms should be in the ground state. So that will be kind of the arrangement. And basically, if we now turn the tuning from negative to positive, you know, if the interaction were negligible, we would just like to excite all atoms, right? That would be the state. But so far, we did not include the interaction. So if we now include the interaction and assume that interactions really blockade, you know, result in a blockade, clearly you cannot excite, you know, all of these atoms. You cannot excite the neighboring atoms. And so in this case, what happens is that, you know, if you just take into account only nearest neighbor interaction, the state you will enter will be this kind of state, this kind of antiferromagnetic type state where every second atom is excited. So this corresponds to breaking the Z2 symmetry, so we call it Z2 ordered, you know, that will be the resulting state. But of course, nothing prevents us from trying to increase the interaction range, and in this case, you can blockade not only a second nearest neighbor, but not only a nearest neighbor, but also a second nearest neighbor. So in this case, you will end up in the state where every third atom is excited, and then, you know, every fourth atom is excited. So that kind of gives you a sense a little bit of what the phase diagram this is, and indeed this was actually explored by my condensed matter colleague Subir, you know, just, you know, about 10 or so years ago. So we would like to explore this phase diagram experimentally, and we'll do it by basically starting in the state with all atoms in the ground state and then trying to adiabatically enter all of these phases. And so to begin with, let's just, you know, focus on the simplest case where only nearest neighbor interactions are relevant. So basically second nearest neighbor interaction are negligible. And then if we, for example, start with a system of just 3 atoms and, you know, start with this kind of situation where first detuning is negative and then try to go slowly across this transition point, then, you know, readily what we observe is basically, you know, is that, you know, is a state like this. So, you know, like it's very easy to understand. So we always excite the neighboring atoms, and then the middle atom is in the ground state. It's just, you know, the most excited atoms while satisfying the Rydberg constraint. Well, 3 atoms is not really a large system, so let's see if we can scale it up. So and we can go to a case of 9 atoms, and in this case we still get this, you know, antiferromagnetic order, or the case of 13 atoms, you know, and still we see a nice order. And this is a single shot image where you start with all atoms in the ground state, and then after this transition, if you image the atoms in the ground state, then every second atom, every second site is empty. That really corresponds to this, you know, creation of this Z2 ordered state. But I claim that our system is programmable. So can we try to explore this entire phase diagram? So in order to do it, we have to try to change the interaction range. And this can be done by either going to different Rydberg states or just doing the same exact thing what we have done, but just bringing atoms a little bit closer. So if, huh?
How do you say it's adiabatic? In what sense?
So we're trying to go slowly across the phase transition.
Okay.
Right, as slow as possible.
Across the Z2 phase.
Yeah, and here exactly, we're trying to kind of go as slow as we can,
Okay.
and that's, in ideal case, this would correspond to perfect adiabatic transition.
So you're approximating it to adiabatic?
Well, I mean, we do what, in the experiment, we do what we can, right? And we hope for the best, but you will see how this ends up, It doesn't always end up very well,
Trying to create the maximum symmetry?
Nah, no, it's just adiabatic passage, kind of many-body adiabatic passage. You can always, so what happens is, so for finite system size, there is some finite gap, right? And if you go slow in the gap, you're in business. But of course, when system is big, this is actually challenging. So here, okay, so here we're entering the Z2 ordered phase, and basically, in order to explore this diagram, the easiest thing for us is just to change the atom separation. When the atoms are a little bit closer, then not only a second nearest neighbor, but the third nearest neighbor will be blockaded. And then, very nicely, we will enter in this state with the Z3 broken symmetry. If we bring the atoms yet closer, then we end up with the state with the Z4 order. So basically just changing, one parameter in essentially, in the same experiment, what we can do is really we can, explore this, entire phase diagram, and essentially, in this case, programmable interaction result in breaking very different symmetries. Okay, so far I've talked about relatively small system sizes. The question is, can we really, check if we are doing adiabatic? Can we check if we're doing coherent kind of physics, or can we go to a larger? And how does this, scale as we go to larger system sizes? So let's focus now on this Z2 order. And in this case, we first start with 7 atoms. So the 7-atom system, we can still simulate many-body dynamics, completely. And what we see is that we see actually very nice agreement, even if we look at many-body state overlap, that's perhaps the most stringent criteria between coherent simulation and our dynamics. So in this case, we create a perfectly ordered state with like 50% overlap. I must say that the only kind of thing that we have done to the theory here, we accounted for finite detection infidelity. So our detection infidelity is actually pretty good. It's about 95%. But once you increase the system size, you start seeing. So we can correct for it, and then this is actually fits very nicely. But of course, what we like to do is really push to larger system sizes. So here, what we do is we look at ground state probability as we increase the system size to something like 50 atoms. And so in this case, what we see, this ground state probability drops, even if we correct for finite detection infidelity. But, even for 50 atoms, we still have like 1% of the cases, we have a perfectly ordered state. So you could say, well, 1% is not too big, but remember, at this point, our entire Hilbert space is 2 to the 51 state. So it's a big space, and yet we hit the state, with kind of reasonable probability. Moreover, if you now look at specific individual states which we measure, we find some kind of distribution, but what we find is that the most probable state which we can create is this perfectly ordered state.
So what happened there with the 40?
Huh?
Why the error there on the 40 are so big?
So what it is now? Let's see. Oops, no, sorry. So yeah, it was just, okay, so there's just not so many kind of realizations, just statistical, right? So basically to get this plot, to kind of really, see all microstates, we had to, do something like 20,000 realizations, right? And
when you said also the theory that takes into account some of the experimental stuff, so do you have a simulation or you have calculation?
well, let's see. So, okay. So, Okay, so basically, okay, so here is, let me just illustrate this, with the kind of, with exact kind of examples of images which we see. So here we start with 51 atoms, all atoms are in the ground state, then do the transfer, and then depending on instance, we see different result, right? And so in this case, we see this perfect ordering, that's this 1% case, but most of the time, what we see is something like this. So basically, we see this long order chain, and boom, there is an error. There is kind of a gain chain, boom, there is an error. So these errors are kind of domain walls. And we can analyze them in multiple ways. I'm not going to show you everything, but one of the ways how we can analyze them, we could just look at domain wall density and variance. And what we see is that, as we go, as the tuning goes from negative to positive, then domain wall density drops. And that indicates that we're entering this kind of ordered state. While at this point of the transition, the variance, starts to fluctuate. System cannot decide in which state it wants to be. So basically, this kind of, behavior is really a kind of a classic characteristic of the Ising-type second-order phase transition. And in fact, by looking at this fluctuation, we can actually even try to nail down this phase transition. And it actually turns out to be in a pretty good agreement with, what Subir has predicted. So in terms of theory, experimental comparison, at this point, you cannot do exact theory, but actually this line is a theoretical model based on the so-called matrix product simulation. So this model actually describes very well the average number of domain walls, but does not describe variance, for example. So, well, still, we can also analyze this kind of number of defects created, So basically, we think that come from two different sources. One is this non-adiabatic excitation. In fact, it can be modeled as a Kibble-Zurich mechanism. And then there another one is we have some conflict to an environment. During its entire evolution, we have a probability of about 1% of spontaneous emission per atom. So it's 1% is small, but we have 50 atoms. So it's already basically our, we have a, likelihood of about, basically, about 50% at least to make a mistake. But that means that we can create these states sometimes where we don't make a mistake. So basically, I hope that this kind of gives you, a little bit of a feeling that, with this approach, we can really have some unique insights into the kind of phase transitions and really study them in great detail. But
for all these instances, you have the same control, right?
Exactly. Yes. Yes. But so what? Okay. So, but what I'd like to now do, just very briefly, is show you about, kind of one discovery that we made with the system, and it really kind of involved taking a system away from equilibrium. So this is actually the first experiment which we have done, with that, and it was immediately a surprise. And so what we'll do here is we'll do the following. So we'll first do our adiabatic transformation, go across phase transition slowly. For example, for 5 atoms, that's the state which we will create. But then here, abruptly change the detuning or this effective Z magnetic field just across the phase transition. Change it to 0, actually. And so you would expect in this case, the system just should kind of relax and should thermalize. But actually, if you look at an individual trajectory, what you see is that something funny here is going on, right? And, the system kind of undergoes some dynamics, and at certain snapshots, it kind of looks like this. There was an initial order, then it became times like this. Then you still wait, and it comes back, and it still keeps going, Well, 5 atoms is not a lot. So let's just see how it works, for different system sizes. So here, for 9, 10 atoms, you still see that there is some kind of life going on after this quench. So for example, for 9 atoms, so this is the state just before the quench. Then sometime later, it kind of inverts, and then it comes back, So we can actually, try to do this experiment in the very long chain with 51 atoms. And, here, it's actually convenient to look at just defect density. So what we see is after the quench, defect density grows. But then instead of saturating at 0.5, which would be a thermal state, it actually exhibits this kind of funny oscillations. So we were actually quite puzzled by this. So these oscillations actually occur also with some kind of funny frequency, which is proportional to Rabi frequency, but not equal exactly. So it's like close to, but not exactly. Rabi frequency divided by square root of 2. And also the time scale of the decay somehow, interestingly matches this kind of second nearest neighbor interaction. So what is going on? What's the physical origin of this? So just for starters, at this point where we quench, we are not at any kind of integrable point. So it's an integrable many-body system. It should undergo fast thermalization. You could say, well, it's a blockaded system, so it's kind of special. But even in this blockade, the Hilbert space actually grows exponential with a number of atoms. So it's a golden ratio to the power of n, interestingly. But it still should actually formalize and saturate. So we have now kind of thought quite a bit about that, try to actually model this theoretically, and indeed, with some effort, we can model this. This is again the so-called matrix product state with quite fairly large bond dimension. But still, what's the kind of origin? Where does this come from? So we have some insights. So, for example, you can take your system of the 51 atoms and actually break it into dimers. So in this case, each dimer, you can think about as a blockaded, kind of 2-atom system. It's effective spin-1 system. In fact, that's how you pick up the square root of 2. Remember, for blockade, there was a square root of 2. But then, of course, this picture completely neglects the interaction between, which is actually equally strong. And so the system like that should also thermalize. So what apparently is happening, and that's we kind of were able to glance it from looking at simulations, which also look at entanglement entropy, is that these dimers somehow, have a tendency of kind of sticking together. So somehow these dimers, don't spread very fast. So basically, entanglement in the system, grows very slowly, and particularly if you just have nearest neighbor interaction, these oscillations seem to never decay. So if you add long-range interaction, you see some decay, but it's kind of, at this point, this is exactly what we observe. So basically, it looks like that these robust oscillations are connected to slow growth of entanglement, likely due to constraint dynamics, and this decay is due to a long-range interaction. But the point that I'd like to make is that the Ising model, the case studied here is really like kind of statistical mechanics 101, right? And the very first experiment, you think everything should be known about this. So the very first experiment that we have done with this system, away from equilibrium, already shows something unexpected. And I think this really just a little glimpse into kind of some new physics, new things to come.
Is this so? It's an interesting result, but it kind of looks very similar to how there's population inversion in a laser, right? When you want the states to come down, that's where you get the coherence from in pop. So do you think there's any connection there?
No, I mean this, the population, so usually for population inversion in the laser, there is no real kind of particle interactions. So it's much more classical, So this one, there is some, there is really this so it's kind of like if you want some flavor, if you heard about many-body localization. So it kind of looks like a little bit like a many-body localization, except for there is no disorder, right? Somehow the system itself, it looks like it's constraints which really do not allow these correlations to propagate. Yeah, no, that's right. So it goes to 0.5. It should be a formal. It's a formalized where indeed here this decays, and this decay is on a scale given by a second nearest neighbor interaction, right? So if you eliminate second nearest neighbor interaction, it looks like it should just decay. It should just persist indefinitely. But of course, we have not, we have not done this. Well, anyway, so I go give you a little bit of glimpse of physics, of what's going on. So we actually have a lot of ideas what to do, certainly in the domain of many-body physics, dynamics, looking at these more exotic transitions where very little is known. But we also start thinking about if we can use this system to really do some kind of things which are useful for information processing. And one specific example I would like to flesh out briefly involves exploring this kind of quantum optimization algorithms. What this is about is kind of a very simple idea, is that if you take, basically any NP-complete problem, you can actually generally map it into ground state of certain Ising model. But generally these Ising models would require some very complex non-local interactions. But there is one specific problem called maximum independent set, which actually really corresponds to exactly the kind of physics which we study in our Rydberg blockade. So what the problem is essentially, suppose you are given a graph, and then in this graph you have vortices, and basically independent set is a set of these excited or colored vortices such that it does not, there is no neighbors, none of the two neighbors are simultaneously colored. So for example, this is one independent set, this is another independent set, and for this graph, this is a maximum independent set. Now the specific kind of case of this is a maximal independent probability set on a so-called unit disk graph. Is basically, you just have a graph, and then you say none of the two vortices should be excited within given distance. So this is one example of this. And actually, if you look at this kind of drawing, you probably think about, oh, I've seen it already. And indeed, you've seen it, for example, in the back of airline kind of magazines, So this is a typical kind of network problem. And actually, it turns out it's really an important problem, practical problem in design of networks. So even for this somewhat restricted set of graphs, it's still NP complete. And actually, if you follow the rest of my talk, you will realize that this problem exactly coincides with finding the ground state of this Rydberg blockade. So we have some ideas to try this out. One approach is to try to kind of, find these states using adiabatic evolution. I think there are some good arguments to say it will be very hard, because for this kind of disordered graphs it will be very hard to hit the ground state. But there are also some very interesting approximate quantum optimization algorithms, and I think they look actually extremely promising and relatively straightforward to implement. So I think it's kind of really an exciting frontier. We're entering this kind of area where basically many body physics and quantum optimization are really kind of go hand in hand. Yes.
So in the way you set up the graph,
Yeah.
you said the two red dots are independent, they're not immediately connected. So are you also enforcing that dots that are, say, two neighbors away have absolutely no influence on a given dot?
Yeah.
Okay. So
Yeah, so it's kind of this graph, it's a card, so it's basically a constraint. All of these problems, they are basically constraint optimization, and they all can be mapped into Ising models, but this one is actually specifically, it's basically mapped directly into something which we can do just directly without any kind of fancy tricks. That's the only kind of idea. All right, so I think, maybe I have 10 or so minutes, so let me kind of, switch gears a little bit, and, in case you heard enough about quantum computers, let me talk a little bit about time crystals. So this actually corresponds to a very different situation, but you would see that it's actually kind of the same spirit a little bit, the same type of physics which we are studying. So what is a time crystal? So the idea, of this comes from Frank Wilczek. And basically he reasoned in the following way. So since kind of space and time should be in some way equivalent, so if we know that we can have spatial crystals, and basically spatial crystals correspond to kind of breaking translation symmetry in space, resulting in this kind of, for example, oscillating correlation function. Why can't we have similar things in time, right? And so this would be if we just have a correlation function which comes back, all the time, is it a time crystal? Well, okay, could say it's not such an unusual thing, the sun rises every morning, is it really a time crystal, Well, not quite. And the key property of the spatial crystals, which, this kind of sun rising, does not have, is rigidity. So basically, in the spatial crystal, once you have this periodic modulation, you try to squeeze it, it does not change very much. So, but in the case of kind of rising sun, imagine some big object hits, Earth or whatever, like this will change the periodicity. So basically, the key property which we would like to have in this example is rigidity. And, Frank has actually, thought a lot about this, and even came with some specific, example where one could maybe see some effect, but his work inspired many others, and people very rapidly realized that in equilibrium, this idea cannot work. It really, it's like perpetuum mobile, basically. So one can prove on a very general grounds that in the equilibrium, time crystals could not exist. But of course, every mathematical proof, has a loophole, and that's here is this kind of assumption of the equilibrium. And basically, these arguments in particular do not apply for the out of equilibrium systems, for example, a system which you derive periodically, and also, do not apply for a system which has both strong interactions, but yet does not formalize very rapidly. And that's the idea behind this so-called discrete time crystal, which was put forward first by Princeton group and also UCSB, and actually Vetica, who is now a postdoc, a junior fellow at Harvard, was one of the pioneers in this field. So this idea was actually realized in two groups, by both my group and Chris Monroe's group, and two very different systems. So let me just show you just a little bit of glimpse how this really works. So basically the idea here is to look for discrete time translation symmetry breaking if you do pulse driving. So suppose you have quantum system and you apply some unitary evolution, but you apply it in a kind of periodic fashion. So suppose you apply kind of many of these pulses, and then naively you would think that the system should respond with the same period. But in some cases, the system, it turns out, can respond with a period which is integral multiple of this kind of period of the initial kind of drive. And so under these conditions, basically, you would have some observable which actually respond with n periodic temporal order, and that's actually kind of discrete time translation symmetry breaking. That's what people call discrete time crystals. Now, these things actually can happen, and they can happen also for classical system, but there's one thing which I would say right from the beginning is very special feature of that, is that this phenomenon should actually be robust both to kind of driving imperfection and also in particular to slow thermalization. And often, things like disorder, which result in localization, could result in such robustness. So to implement this idea, we actually made use of artificial atoms, which are kind of atom-like impurities in diamond. So this work on control of these impurities actually is something we have been doing over the last more than 10 years, and these impurities are now being explored for both applications in quantum information, but also they can be used for things like sensors. And in particular, in this work, we use this so-called nitrogen-vacancy color center, which is basically the point-like impurity where in diamond you replace like one carbon atom with nitrogen and just have a kicked out a carbon atom of vacancy, and basically this behaves like a kind of molecular-like color center. So for example, if you start with the reasonably pure sample, what you see, you kind of see these things like individual kind of stars in the sky. These are individual color centers, right, in this diamond. And what's particularly important about those is they have non-trivial spin states. So in the ground state, they are spin 1 particles, and they can be rotated, these spins, with microwaves. They can be polarized optically and read out optically. So it turns out one of them, in one of the states, this impurity fluoresces faster and another one is slower. And finally, it turns out quite remarkably, even under ambient room temperature conditions, these spins have long coherence, have like a millisecond long coherence. And basically, this, we use these guys as a qubits, and so this is one attempt to create like a regular array of those, similar to what we've done with atoms. So here, what we do, we start with a pure bulk diamond and just bombard this diamond with nitrogen ions and then try to convert them into nitrogen vacancy centers. But what you see here is that there is some kind of order here, but it's not perfect. And so here, you cannot use these wonderful tricks that Manuel has come up with to kind of move these guys around. So we kind of have to live with this disorder. And the question which actually we are trying to explore is, can you really control this disordered system? Can you somehow try to get something meaningful out of that? So to realize, this, to explore this time crystal, we actually took this kind of problem to extreme. We worked with the sample which has so many impurities that it literally looks black. And in this case, basically the distance between this nitrogen vacancy center is something like 5 nanometers. So this sample has also a lot of disorder. So for example, this results in a 1,000-fold broadening of electron spin lines. But basically, if you then study this sample and really try to understand what's going on, remarkably you find that all of these processes can be described by this Hamiltonian, which is actually something that you already seen. So it's a kind of Ising Hamiltonian with flip-flop interaction. The only important thing is that here, because it's dipolar, is 1 over cubed. So this is actually how the sample looks if you start shining it at this with green light. So it actually really starts looking kind of pinkish, which is very cool. So it's because NV centers are the most dominant impurities. And this is the people who made this to work. So to demonstrate this time crystal, what we actually do is we polarize the spin along the x direction and then start applying pi pulses. And so there is a trivial example where you would see kind of period doubling, is where, basically you just apply perfect pi pulse, goes x to minus x, back to x, right? So it's, you apply 2 pulses and, the spin comes back. So it's period doubling. Is it time crystal? No. Because if you, for example, apply the pulse which is not perfect, you under-rotate or over-rotate, and basically what it results is that, there is a phase lag. So basically, this kind of time crystalline order will not be stable. But actually, remarkably, what happens is that if you interrupt these periods of these pulses with just letting the system interact, letting spins interact, what happens is that, basically during this interaction time, the system can kind of adjust itself such that it kind of evolves in such a way to close this trajectory. And this actually is exactly this kind of, time crystalline order. And once again, the important thing is that it should be robust to imperfections and also to the heating. So here is a demonstration. So basically what we do here, we apply the unitary, the periodic unitary, which consists of the pi pulse and then some interaction period. And initially we make this interaction period very small. What we see is that we see this, kind of periodic modulation, but then, it's because our pi pulses are not perfect, this actually, this periodic up, down, kind of order decays. And now we can, by default, just by hand, change these pi pulses. We can just under-rotate, and then what you see is that we easily, even destroy what we have here. So, in fact, if you look at a Fourier transform here, you don't even see a peak in the middle. So this is exactly this kind of phase lag, which I mentioned. But actually, if we now just make one simple change, just increase the duration of this waiting period, of this interaction period, what we find is that actually this order, original order, comes back and in fact, lasts even longer than in the case when we had nominally perfect pulses. So that's actually this kind of long, up down order is really the signature of this discrete time crystal. So I don't really have kind of time to discuss how exactly this works. But we do some tricks here. We actually engineer the interaction. So in fact, during the free evolution, our interaction is an Ising-type interaction, it turns out. And actually, this Ising-type interaction, provides this effective field, which precisely results in this kind of under-rotation and over-rotation. So we studied this system in various different ways. So it turns out that there is actually quite sharp crossover from this discrete time crystalline order into the non-ordered state. And some of this crossover you can understand by just looking at this kind of simple block sphere, the mean field picture, this initial result. Some of that requires much more careful analysis. It turns out that this actually, what we see is the so-called critical time crystal. So it's kind of the time crystal which is right on the boundary between being stable and unstable. But at the end, it's actually, really we see some quite robust, crystalline order, and also I think what we see as this discrete time crystalline order is very sensitive probe of quantum dynamics.
But is there any symmetry breaking there?
Yeah, it's discrete, it's a discrete time symmetry. And so you see the response every second time, Or we have also seen where every third time, we can see n equals 2 and equals 3 time crystal. So both of them is actually really show the symmetry break. Time translation, discrete time translation symmetry break. Okay, so I kind of wanted to maybe, okay, let me just give me maybe 3 minutes, Manuel. So it was special, you know, since we had so much discussion. So let me just show you that this time crystal is not just a curious effect, but in fact it can be potentially maybe useful for humankind. And the way actually I would like to the point I'd like to make is that, you know, one contribution we as physicists make to other disciplines like biology or medicine is we come up with tools. And, you know, for example, you look at this list of tools, you know, these all tools which came from physics, you know, and they basically transformed the medicine. So this kind of quantum control of individual atoms or atom-like systems, you know, it's also, you know, we also develop the tools, and actually these same tools which help us building quantum computers are also useful for things like metrology and sensing. And so in particular, you know, starting from about like 10 years ago, we use these NV centers as very local sensors of things like magnetic field. So the idea here is that if you bring NV center, because it's a point-like, atom-like impurity, if you bring it very close to a target, like a single protein, then, you know, you start already seeing kind of magnetic signals from nuclei and from all sorts of other things. Now, of course, you know, there are many different nuclei here, and, you know, if you just look at the kind of noise, you know, you see everything. So basically what you need to do, you also need to be able to zoom in on certain frequencies to really sense one specific nuclei. And the way how we do it is applying this kind of periodic pulse sequences to basically synchronize this up-down, you know, electron spin with the kind of frequency of the signal which we would like to detect. So it's kind of like a lock-in, you know, quantum lock-in detection, if you want. And actually, this, you know, technique, you know, actually can be very, very powerful. So, for example, a couple of years ago, we actually could really detect NMR signals and do NMR spectroscopy from just individual molecule from a single protein. Actually, I must say it has been a lot of fun for me personally, because this kind of idea allowed, you know, us to really go in different directions. So, for example, we could control viability of the cells, you know, by just doing this sensing, by using nanocrystals inserted in the cells. We've also been able to study kind of new materials using this approach. And for example, by looking just, you know, by peeling, you know, the you know, materials which you can control layer by layer, we could actually see some small shifts of line which really tells about how atoms rearrange kind of really in a single atom, the single atom layer, the single atom sheet. So there are many, you know, exciting developments, and I think some of them, in fact, already being commercialized. So there are some of my students actually have a company focused on application of these ideas to medical diagnostics. So how does this work connect to time crystal? So one big limitation of this technique, and I would say metrology in general, is that you would like to have a lot of particles to have high signal. But if you bring a lot of particles together, like in these centers, they start interacting to each other. They start sensing each other instead of sensing the target. So basically, the idea of the time crystal is to use this kind of strongly correlated matter really to improve coherence, right? To use interactions to actually lock them together if you want. And in particular, this kind of time crystalline order can actually be used to stabilize this so-called Schrödinger cat states, which actually are known to be maximally sensitive to perturbations for sensing applications. And in fact, you know, the fact that we can already, you know, see an extension of the you know, of the sort of lifetime, you know, is a kind of first glimpse into that. And so we believe that in particular for this application of NV centers, this can be really, you know, useful approach. And in fact, we already have, at least theoretically, developed a couple of protocols which we hope to test experimentally soon. So I think this also shows you another exciting frontier. We are basically, you know, we can start thinking about using correlated quantum matter for applications in metrology, like sensors, maybe even clocks, maybe precision measurements, or maybe even, you know, axion detection. I think there are ideas. So anyway, so I think, you know, at this point, I would like to thank you for your attention.
Questions?
Can you get any insight into the thermalization and the quenched
Yeah.
Rydberg system
Yeah.
from looking at thermalization in classical many-body systems that are constrained or frustrated in some way, like your Rydberg system?
So this is not completely clear, I would say, you know. So, and, you know, so like at least our current understanding is that, you know, what is happening is that somehow due to these constraints, so I think the statement number one, so what's clear is that once you have constraints, this, you know, general thermalization arguments simply should not hold, right? Because usually, you know, so we say that we start at infinite temperature system, which effectively for our, you know, quench, and it's true, except for it's low temperature compared to constraint. So there is kind of a hierarchy of the scale. And so basically what this constraint does, it makes certain part of the Hilbert space inaccessible. And like, okay, I mean, you know, I'm not speaking scientifically, but it looks like this kind of inaccessible state almost acts as a kind of a wall, which these excitations cannot cross. So I think entanglement probably plays a role here because you create this kind of singlet pairs, but you know somehow this entanglement grows slowly. So you know I think I'd say probably no, but you know. So you're thinking about this device, right? Right, that's one thing, right, which does not thermalize. But you know this is not this you know, yeah. Oh.
Quite quickly.
Yeah. Manuel, you should be.
I thought it was.
Yeah.
Well, a sort of related question. You showed a simulation for 21 atoms,
Yeah.
the dynamics after
Yeah.
the machine Rydberg.
Yeah.
I assume that was the Schrödinger evolution.
That's
of
correct,
the
yes.
Hamiltonian bit.
Yeah, yeah.
Is that about as large a system as you can simulate?
Yeah, for dynamics, it's about as large a system, yeah. And actually, it's already kind of remarkable that you can do this, and because here you can use this constraint to cut down your Hilbert space a little bit. So, I mean, dynamics is very hard to simulate. You know, you could maybe go to like 25 atoms, but, you know, it's okay. It becomes, you know, very, very challenging, yes. So, and I think that's what's exciting, right? We really enter the area where we really, you know, can not do the simulation, at least not exact ones. I think it's actually very cool.
More questions?
Yeah.
So with these time crystals, you have one order parameter which is sort of recurring after some number.
Yeah, exactly.
If I were to define like some other order parameters that are thermalized, are you getting like some rethermalization in different states, or is it the whole system is not thermalized?
Well, okay, so that's actually a very good question. So can you describe, so you have, you know, certain Hamiltonian, which maybe have some conservation laws or something like this. Can you think about this as a kind of prethermalization? And actually the answer is no. And the reason is, you know, in this specific case, the reason is that with respect to this, you know, effective Hamiltonian which we have, our initial state has infinite temperature. So it should really, you know, if it were prethermalization, it really should decay. So basically, what we believe happens here is this kind of critical, so-called critical dynamics. So we have disorder, which normally would localize the system. It would actually create an MBL. But we have also long-range interactions. And these long-range interactions, basically, you know, in the 3 dimension is 1r cubed. So it's precisely the boundary between localized and thermalizing system. And you know that results, for example, in a sort of informalization, which we actually scale like a power law with disorder-dependent exponent. And actually, that what is kind of to explain a phase diagram. That's exactly the ingredients which we used.
Okay, so one more question.
There are 2. Okay.
So the question, I think it's really fascinating what you're doing on the biosensing
Yeah.
there. Do you see in the future that all of these light sources, LCLS, etc., the studies that they're doing on such biomatter that you and characterization of such that you can combine with what you're doing here, or is this? Or you don't see any
So I would say,
use of that?
No, I would say it's kind of complementary. So I mean, like, so one kind of big goal, which I would actually, right from the get-go, I say we do not know yet how to accomplish, would be to really try to kind of, determine the structure of the proteins which you cannot, crystallize. So something like membrane proteins. And please don't ask me questions about this. So I'm told that this is one example where, like you would really like to kind of, understand them. And you can try to get the information about those kind of systems from different approaches. So one is from this very kind of, well, I think the technique which actually got a Nobel Prize, at cryo-TM this year. Another one is, this like, what's it called? SLS? Yeah. LCLS. So, but what these approaches actually tell us about kind of a geometric structure. There is no like chemical specificity to this approach. Our approach, actually, we can, in principle, learn about where exactly each atom, type of atom, where it's sitting. So basically, I would say at the end, if you really want to tackle some of these very challenging kind of problems, you'd probably need to, combine information from all of them, and that's maybe the so there was one maybe question from the student, you should have said. Yeah.
One more.
Yeah.
So real quick, you mentioned briefly that the accessible Hilbert space for Rydberg chains, both for its dimensions, scale, essentially as the golden ratio to the power n. Is there any significance to the fact that that's the exact same scaling as for Fibonacci anyons?
Yeah, no, that's not a coincidence. So it turns out that basically, so this model you can always kind of express in terms of Fibonacci anyons, but generally you have like some complicated interactions. But actually, it turns out there are some parts on this phase diagram, in which basically the ground state of the model is exactly ferromagnetic Fibonacci anion model from this famous paper, from the station Q, they've been talking about. So the only thing, and it's actually, I think it's an intriguing connection, which we certainly, hope we will explore. But the only, issue is that, like when people thought about these Fibonacci anyons, everyone is thinking about equilibrium. So the real interesting kind of challenge, for you guys and for everyone is to think what will be the signatures of these Fibonacci anyons if you go away from equilibrium. How will these Fibonacci anyons thermalize? Perhaps one could understand even what we observe already with that. So maybe that's.
Before everyone runs away, we have the PMA fall gathering. Also non-PMA members, I see a few invited to come. And with that, I would say we say thank you again.